Hello, my YouTube viewers. Myself is Dr. Vadiraj Bitango, Assistant Professor, Sri Jagadguru Tontadaria Government First Grade College, Mundargi. So, in this video, I am discussing about Maxwell's thermodynamical equations. Among the series, this is my first video regarding this Maxwell's thermodynamical equations. This is for BSc program, physics subject, BSc second semester, CBCS system, and we are dealing in a paper of thermal physics and fluid mechanics of unit 1. Learning objectives of this discussion is to know the concept of Maxwell's thermodynamical equations, to understand the meaning of all terms involved in the Maxwell's equations, usage of laws of thermodynamics, applications of Maxwell's thermodynamical relations. Session outcomes: knowledge of Maxwell's thermodynamical equations, understanding of each terms in the equations, usage of laws of thermodynamics, applications of Maxwell's thermodynamical equations. Prerequisites for this discussion is we should have concrete idea about the first law of thermodynamics, concept of second law of thermodynamics, and mathematical partial differentiation. Syllabus for this discussion is Maxwell's thermodynamical relations with the derivations, applications of Maxwell's thermodynamical relations. One is to derive Clausius-Clapeyron latent heat equation and Joule-Thomson's expansion. So in this discussion of series 1, I am deriving only general form of Maxwell's thermodynamical equation. For this, we know the first law of thermodynamics as dH is equal to du plus dW. That is, whenever heat is supplied to a system, it is used for the two purposes. One is to increase the internal energy, that is du, and to do the external work. This external work dW can be written as PdV. Therefore, equation becomes dH is equal to du plus PdV. Or we can write this equation in terms of internal energy as du is equal to dH minus PdV. This is first law of thermodynamics, where H is heat, U is internal energy, W is external work, P is pressure, and V is volume of the system. And from the second law of thermodynamics, that is the definition of entropy, we know Ts is equal to dH upon T. That is, change in entropy is the ratio of change in heat to its temperature. Or this equation can be written as dH is equal to T into ds. This dH value, if we substitute in the first law of thermodynamics, we get du is equal to Tds minus P into dV. Here, three variables. One is S, entropy, U is internal energy, and V to be a volume, to be a function of independent variables x and y. Therefore, we can write each perfect differential into sum of partial equations with respect to x and y. Like this, entropy, change in entropy Ts is dou S upon dou x, keeping y as a constant, into dx, plus dou S upon dou y with keeping x as constant into dy. This total differential ds is partial differentiation first with respect to x, and second term is with respect to y. That sum of with respect to x and sum of with respect to y, that must be equal to total differential ds. Similarly, we can write u and v perfect differentials in terms of partial differentials are given by internal energy du is given by dou u upon dou x keeping y as a constant into dx plus dou u upon dou y with keeping x as constant into dy, and dv change in volume is given by dou v upon dou x keeping y as constant into dx plus dou v upon dou y keeping x as constant with respect to dy. So these are the variables, independent variables ds, du, dv. These ds, du, dv terms we should be substitute in above equation number 1, that is du is equal to t ds minus p into dv. We get equation is like this: dou u upon dou x keeping y as constant into dx plus dou u upon dou y keeping x as constant into dy is equal to t into ds partial form is given by dou s upon dou x keeping y as constant into dx plus dou s upon dou y keeping x as constant into dy minus p into partial differential of dv. That is dv is given by dou v upon dou x keeping y as a constant into dx plus dou v upon dou y keeping x as constant into dy. Now we can compare, we can collect the terms of RHS terms of dx separately and dy separately. We will get like this: dou u upon dou x keeping y as constant into dx plus dou u upon dou y keeping x as constant into dy is equal to LHS is remains same. Now we should be collect the first term of RHS and that is the third term of RHS at dx, and then dy term separately. We get t into dou s upon dou x keeping y as a constant minus p into dou v upon dou x keeping y as a constant into dx minus t into bracket dou s upon dou y keeping x as constant minus p into dou v upon dou y keeping x as constant into dy. So therefore we have collect the dx terms separately and dy terms separately. Now we should be compare LHS of dx terms, one equation, collect the dy terms, another equation we are getting. So now we are comparing dx term and dy terms and we are writing the equation separately. So we are writing dx term dou u upon dou x keeping y as constant is equal to t into dou s upon dou x keeping y as constant minus p into dou v upon dou x keeping y as a constant. This is equation number 2. Similarly, we can write the comparison of dy terms, that is dou u upon dou y keeping x as constant plus is equal to t into dou s upon dou y keeping x as constant minus p into dou v upon dou y keeping x as constant into dy. This is third equation we have got. Differentiating the above equation, that is equation number 2 and equation number 3. Equation number 2, now we are differentiation with respect to y, and equation number 3 with respect to x. We got like this: dou square u upon dou x into dou y, dou t upon dou y keeping x as constant, dou s upon dou x keeping y as constant plus t into dou square s divided by dou x dou y minus dou p upon dou y keeping x as constant, dou v upon dou x keeping y as constant minus p into dou square v divided by dou x into dou y. Now we can write second equation with a differentiation with respect to x. We get dou square u divided by dou x dou y is equal to dou t upon dou x keeping y as constant dou s upon dou y keeping x as constant is equal to plus t into dou square s divided by dou x dou y minus dou p upon dou x keeping y as constant into dou v upon dou y keeping x as constant minus p into dou square v divided by dou x into dou y. The change in internal energy brought by changing volume and temperature, whether volume is changed by dV first and T vice versa, there is no difference. It means in the second order partial differential equations, the denominator dou x dou y, if we interchange, they are same. It is given by dou square u divided by dou x dou y is equal to dou square u divided by dou y dou x. Therefore, equating the above two equations with the RHS, we get a very big term. Hence, if we equate the above two equations, we get dou t upon dou y keeping x as constant, dou s upon dou x keeping y as constant, plus t into dou square s divided by dou x into dou y minus dou p upon dou y keeping x as constant, dou v upon dou x keeping y as a constant minus p into dou square v divided by dou x dou y is equal to dou t upon dou x keeping y as constant into dou s upon dou y keeping x as constant plus t into dou square s divided by dou x into dou y minus dou p upon dou x keeping y as constant into dou v upon dou y keeping x as constant minus p into dou square v divided by dou x into dou y. Now cancelling the equal terms. So I have mentioned the equal terms in the red color. So cancel the red color equal terms. We get dou t upon dou y keeping x as constant, dou s upon dou x keeping y as a constant minus dou p upon dou y keeping x as constant into dou v upon dou x keeping y as constant is equal to dou t upon dou x keeping y as constant, dou s upon dou y keeping x as constant minus dou p upon dou x keeping y as constant into dou v upon dou y keeping x as a constant. This equation is called generalized Maxwell's thermodynamical equation. Here x and y are two variables. They are changed according to pressure, volume, temperature and entropy will be changes. And it can be written, it can be remembered very easily. It is TSPV type. TSPV. So first term is T, second term is S. Third term is P, fourth term is V. The same TSPV. So in the right side is also TSPV. And the bottom side is first left LHS is dou y into dou x, dou y into dou x. Right side is reverse, dou x upon dou y into dou x upon dou y. Whenever the denominator is y, then keep the constant as opposite, that is x. Therefore, the first term of second part is dou s upon dou x is there, we should keep y as a constant, minus dou p upon dou y, keep x as a constant, dou v upon dou x keeping y as a constant is equal to dou t upon dou x keeping y as a constant, dou s upon dou y keeping x as a constant minus dou p upon dou x keeping y as a constant into dou v upon dou y x as a constant. So we can remember very easily TSPV, TSPV, dou y, dou x, dou x, dou y. In this way, we can easily remember this generalized Maxwell's thermodynamical equation. So this is all general Maxwell's thermodynamical equation. Thank you for hearing my Maxwell's thermodynamical equation with your leisure time. Thank you one and all.